Okay. Hello everyone. My name is Xinbo. I am a fourth year math major student at the University of Texas, Austin. And today, December 4th, I gave a talk in the university that talked about this subject of schemes and how it relates to varieties that the other presenters have presented earlier were talking about. So they have given an awesome talk. Today, this is a re-recording of what I'm planning to talk about, but unfortunately, due to the time limit, I don't have enough time to elaborate on all of the points. So I am trying to re-record presentation, and hopefully this one will be longer and you can follow along better. So let me begin by defining affine n-space. So an affine n-space over a field is just equal to your k to the n as a set. And the associated ring with it is the coordinate ring, which is the polynomial ring with n variables over the field k. And I put a topology on it. This is called Zariski topology. So for a polynomial, let z of f to be the zero set of f. And for a subset t of A, we can define z of t to be the common zeros of all elements of t. And this is the explicit formula for it. Um, and z of t equals z of I if I is generated by t. And sets of form zt are called algebraic sets. And I define a topology on this affine n space by declaring the closed sets to be the algebraic sets of the form zt. And by these following observations over here, you can actually see that it is a well-defined topology, so I'm not tricking you. For example, let's consider A1, the affine line, where the coordinate ring is k adjoint x. So A here is a PID, principal ideal domain, and then the element f inside my coordinate ring A could be factored in linear terms. So f of x could be expressed as c times x minus a1, x minus a2, blah, 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 up to x minus an. And we deduce that z of f is actually a finite discrete set of points. And um, in this case, Zariski topology actually coincides with cofinite topology, which people might have learned in the first course in topology, but they don't really know where to make sense of cofinite topology at least when I was taking my own topology one course, this topology didn't make sense. And in particular, this topology on this affine line is not Hausdorff, and my affine one space is irreducible. So I can also define a notion of variety. So affine variety is just an irreducible subset of a to the k with the Zariski topology I just defined. And a quasi-affine variety is just an open subset of an affine variety. Um, and there's a one-to-one order reversing correspondence between algebraic sets and AN and radical ideals in the coordinate ring. An irreducible algebraic set corresponds to prime ideals. So be careful. So this statement actually is a consequence of a purely algebraic theorem called Hilbert's-Nullstellensatz. Uh, and I wouldn't elaborate on that further. So for example, we can consider the coordinate ring which is the polynomial ring with n variables. So maximal ideals of this ring actually corresponds to minimal irreducible algebraic sets, which are points in the end. So be careful. So I'm really just using this fact that it's order reversing. So maximal sets maximal ideals kind of corresponds to minimal sets. And so I want to define regular functions. So that why be an affine variety? So a function from this affine variety to k, where I put the Zariski topology on k by saying k is just the same as a1. This function is regular at a point in y if there exists an open set u in y and g of h in a, the coordinate ring where h doesn't vanish on u such that f is locally a quotient of these two elements. And a function is regular if it's irregular at all points in y. And you can actually see that in Zariski topology, regular functions are continuous. Um, And now I can give you a description of the category called varieties over K. So objects in this category is just any affine, quasi-affine. I haven't mentioned projective or quasi-projective for simplicity of this talk, but you should be those are also included as objects in varieties over K. And in particular, any projective variety actually has a affine cover. So and morphisms of varieties are just continuous maps such that for all open subsets V and Y and a regular function defined over V, it pulls back to a regular function of phi inverse of V as an open subset of X. And now let's build our way towards schemes. So the first notion I'll define is the notion of presheaf. So let X be a topological space. A presheaf F of abelian groups on X consists of the following data. So first, for every open subset U in X, I give you an abelian group F of U, and for every inclusion V of V inside U of open sets of X, a morphism of abelian groups called U rho UV from F of U to F of V. So this rho UV in reality is oftentimes called the restriction maps because when I have an inclusion like this, the map inclusion map is going like this, but this is really like saying expressing the contravariant nature. So f of u is sort of u contains v. So like u, let's say this is u and this is v. So it's really restricting onto a smaller one intuitively. But this doesn't have to be the restriction morphism, and it doesn't make sense when f of u and f of v have no relationships at all. Um, um, Such that f of the empty set is 0. The restriction map from U, any open set, to itself is the identity. And if I have a chain of inclusion of open sets, then the restriction map is satisfy this co-cycle condition. So what I'm really saying here, if you view it as a functorial way, is that a presheaf is actually just a presheaf F. It's a functor from the poset defined in my topological space to the opposite category of your favorite algebraic structures. So here I can put, like, for example, commutative ring, and in here definition I can put abelian groups. They're really the same, but because it's contravariant, so if you want a covariant functor, it's you put an op. If you don't want to, if you can say it's contravariant, then you don't have to use the opposite category. So the poset structure is given naturally by saying a partial order exists if you have this inclusion relation. So V is sort of smaller than U if and only if V is included in U. And a sheaf on X is nothing but a presheaf that satisfies two extra conditions. So first, if I have an open set and V of I is an open covering of U, then if S in F of U is an open set, that S restricts to V of I. So this terminology here really means I apply the restriction map rho UVI to S. And if it's 0 for all VI, then I can conclude S equals 0. And if Si is our sections in smaller open sets in f of vi for each I, such that for all I and j, Si restricted to Vi intersect Vj, where as the same philosophy I'm actually applying the restriction map, equals Sj restricts to the intersection, then there exists S in f of u such that S restricts to V of I equals Si for each I. And the first property tells us that this S is actually unique. And there's really a intuitive example for this notion of sheaves. So for example, I can define the sheaf of smooth functions. So consider Rn with the standard topology, which are described by open balls of radius, are the one that you're very used to in a first course in analysis. Then smooth functions on Rn actually form a sheaf. And explicitly, I can just define it like this. So I can take f of u to be smooth functions defined on the open subset u inside Rn. And I can just denote I denote this sheaf of smooth functions as C infinity Rn. So this is really one of the standard notations that people use. Um, so for example, I hope if you're thinking the constructions are too abstract, this is the mental picture to keep in mind. So if I have, let's say this is R2, and I have two open sets U and V, and the intersection U intersect V, and I have a function defined over U, and I have the function smooth function. They're both smooth, of course, defined on V, which you can see as like the hills over there. Um, and if they agree on this intersection over here, then actually I can glue those functions together to form a function over union V, and it's smooth everywhere inside union V because the smoothness property is examined locally. Um, so I want to introduce the notion of stock because every time most of the time when I learn about algebraic topology, a lot of the concepts are involving like local properties. For example, smoothness is a local property. And when you verify something is, for example, the definition of what I'm going to give you as schemes or locally ring spaces are like schemes, I think it's more proper. That is something that is locally isolated, have a local model of something else, something affine or easier to define. So I want to start building this local language by introducing the notion of a stock. So suppose f is a presheaf on x. I can define a stock fp at p and x is the set of germs of the form us, where S is a section in U, and US is equal to VT if and only if there exists an open subset W, which is a subset of U intersect V such that SW is equal to T restricts to W. So the mental picture to keep track of here is this. So let's say I have two functions I drew over here that is wildly different outside of this open neighborhood that I drew. But besides that, they're identical over this smaller open subset that is around P. So I can conclude that they actually represent the same stock, despite the wild behavior outside of this. Um, so that's really transforming something global into just examining, like magnifying something around P such that you don't really care about the rest of the world. You're just magnifying, using a magnifying glass to recognize the neighborhood around P and its behavior over that neighborhood. Um, so actually, if I have a morphism between, I have to introduce it here. Sorry. So let f and g be presheaves on X. A morphism f to g is a collection of morphisms. Sorry, I have a typo here, so it's really phi of u from f of u to g of u, making the following diagram commute. So you can say, because previously I introduced the notion of viewing presheaves as functors, so you can say that, if I have a functor f and g, they're like presheaves. Then a morphism phi between f and g is just a natural transformation between the functors, which is the same as saying it makes this diagram commutes over here. And so there's a natural question that arises, and it's a very important concept actually. So suppose I have a continuous map of topological space, X and Y, and I suppose I have a sheaf over here. Let's denote F, and I want to get a reasonable sheaf over here that has reasonable information that uses F basically. So for any sheaf F on X, I can define the direct image sheaf F lower F on Y to be this described by this following formula over here. And you can actually verify this gives you a sheaf because this formula is oftentimes like it's always a pre-sheaf, but you have to define you sort of have to verify that it's actually a sheaf. And the good news is this is very easy definition because you can just write what are the sections. But one caveat is that this is not a good description for the stock because as you can guess over here. So I have an open set over Y, but this doesn't actually um, go through all the open subsets around a point. So you can imagine that it's going to be a little bit hard to describe the stock of this direct image sheaf. But let's say in this and conversely, sorry, I have a sheaf defined over y, and I want a reasonable sheaf defined over x. So for any sheaf G on Y, the inverse image sheaf F inverse G is the sheafification of the following pre-sheaf formula that I just gave over here, where U is open in X and limit. This is actually the direct limit taken over all open subsets V containing F of U. So this is really a hard, like it's going to be a little bit hard for you to write out the sections, like the elements of F of, let's say F of U, because it involves something complicated called like sheafification. Well, the nature is really not complicated because the philosophy of sheafification is this. So functions are naturally subject in glue, and you're trying to make something out of you're trying to make something is not a sheaf but is a pre-sheaf into a sheaf. So the natural thing to do is consider the functions uh, appropriately defined so that you can glue them just as topological space maps. Maps of topological space. And the limit is taken over all subsets containing f of u, so you can maybe guess that the stock in this case is easier to write out. In fact, it is. So I want to talk about as well, like what the morphism between pre-sheaves is actually, because I've tried to convey this information that a lot of the things in algebraic geometry is really local. So actually, if I have a morphism, let's say phi from from f to g, of course they're all sheaves over x, or pre-sheaves. Then actually, if let's just live in the world of sheaves. So this defines a map, very natural, very intuitive map on the stocks. So I denote the map on stocks as phi of p. So this map is defined by what you would guess to be so. So like if I have US, then I map this to what I would map over there. So like it's mapped to phi U of S. And you can verify that the properties of phi is oftentimes equivalent of properties of phi of p. For example, um, um, injectivity or surjectivity transfers well between phi with phi p. So if for all p. But the thing is, because of the functorial description, so something that you need to be a little bit careful is that this doesn't. So this injective is equivalent to phi of u being injective for all u open in the X, but the caveat surjective does not translate. It has to do with the thing that taking like the global section of the functor that takes the global section is not right exact, but it's left exact. So this is kind of what I'm trying to say to you. So like a property of a map between sheaves is really local. So you can examine the stocks and conclude properties of the original map between sheaves. Um, okay. Um, Let me define ring spaces. So a ring space is just a pair of topological space and a sheaf of rings O of X on X. A morphism of ring spaces from between two ring spaces is just a pair F sharp of a continuous map F from X to Y and a map F upper sharp from O of Y to F, the direct image sheaf of F lower star OX of sheaves of rings on Y so that you actually can compare. So this map actually has an equivalent description, is that you can say, well, F upper sharp could be, F inverse O of Y map to O of X. And in situations, you might want to use one over the other. So this has the advantage of easy descriptions of sections. While this has the easy description, when you look at this map, the induced map of stocks, and you have to do a couple exercises to absorb this nature. So I wouldn't do it in the short period of the talk. Um, And a locally ring space is a ring space where the stocks of the structure sheaf O of X at any point is a local ring. And the morphism between locally ring spaces is just a morphism of ring spaces inducing local morphisms between stocks. So I said that stocks are local rings. So local morphism here really means that my map respects the unique maximal ideal. So what's really saying is, for example, a map F from A to B of local rings, or I call this a local morphism if F of the unique maximal ideal is a subset of the unique maximal ideal of B. Okay, so for example, this abstract, seemingly nonsense locally ring space it could give us an alternative interpretation of manifolds, which we think are really geometric, depending on your background of math. If you have taken differential topology, you should be able to uh, argue for me that this is a really geometric space. Um, so we can consider the spaces X and Y equals Rn with the standard topology. As usual, standard topology means the one that you are already very used to in a first course analysis. It's equipped with the sheaf of smooth functions. And let F and F sharp be a morphism of locally ring spaces between them. Um, for each point P and X, the stocks C infinity X at P and C infinity Y at F of P are both local rings, with the unique maximal ideal to be elements which vanish at P or F of P respectively. And in this case, it actually you can compute from the local homomorphism of rings of local rings condition that the map F upper star is actually the pullback map of smooth functions. So it justifies my choice of notations over here. So why did I not write like something like this? F and phi, where phi is a sheaf map of sheaves where you only use the information about the direct image sheaf, but yeah, so what, right? And this example really justifies the choice of using the same letter. So I think it's just good to put it here, and it clears some clouds of some abstract nonsense. What is a locally ring space? And you can view them really as locally ring spaces. And let me define affine schemes now. So I want to give you a set first. So consider ring A. I define a set to be spec of A, to be the set of all prime ideals of this ring. So I need to put a topology on this set. So let A be an ideal of A and define V of A as a subset of spec of A to be the set of all prime ideals which contain A. And by those observations that I wrote over here, you can confirm that it actually gives me a topology by declaring VA to be the closed sets. Just as in the case of varieties, where we define the zero set, here is the same philosophy because the observations are highly, really similar. But you don't really need this. This is really for like order reversing correspondence part. Remember, in varieties we have this order reversing correspondence, um, and I want to define a structure. I want to put a sheaf on this topological space. So what do is I define the sheaf to be for an open subset U inside a spec of A, using the Zariski topology I defined over here. Define O of U to be the set of functions S from U to the disjoint union of P. Remember, P, each prime ideal is a point in this topological space. So P in U of the localization of the ring A at the prime ideal P. So what it really means is that you invert all the elements outside of the prime ideal, such that for each P, the function of value of S at P is in the localization of A over this prime ideal P, and S is locally a quotient of elements of A. So explicitly written out, it's something like this, which I'll not spend a little bit more time on it. So spectrum. Now we have the essential parts to define a spectrum. So a spectrum of a ring is really a pair consisting of the topological space spec of A together with the sheaf of rings O defined above. And we write this as a pair. So spec of A is a topological space. O is the sheaf of rings that I just defined above. Actually, we have a correspondence. We have an equivalence of categories. So this op is really just keeping track of the order reversing correspondence. It's You can forget about it if you're more comfortable. You're comfortable with it. So the map from C commutative ring to affine scheme is given by mapping the ring to the spectrum of this ring, and affine scheme to commutative ring is given by X mapping to the global section of this affine scheme. On the structure sheet. And I haven't defined what an affine scheme is, so it's really like kind of okay. So yeah, what is an affine scheme then? So an affine scheme is just a locally ring space X O of X, which is isomorphic as a locally ring space, so the spectrum of some ring. And a scheme is a locally ring space locally isomorphic to an affine scheme. And we call X the underlying topological space of the scheme X O of X, and O of X its structure sheaf. A morphism of schemes is a morphism of locally ring spaces. So, as you can see, I've already assembled the essential parts to define schemes, and this definition reminds you of the local philosophy that I've been always talking about. Like schemes are really, it's a really like okay, for each point I have a neighborhood such that this open neighborhood is locally isomorphic to something affine. So keep track of this philosophy. Um, and notation, we can denote X. We now denote X to be X with its structure sheaf if X is a scheme, and we denote the underlying topological space to be SP X. So what is a scheme over K? So a scheme X over K is just itself, which is a scheme together with a morphism of schemes, X the spec of K. And a morphism between schemes over K is a morphism of schemes compatible with a given morphism to spec of K. And I consider myself as a geometer, so I would draw a lot of diagrams, and I found it easy to explain this concept in terms of diagram. For example, and in other words, what I said above is that this diagram commutes. And the fact that it's a sheaf map actually tells you that the global section of X of O of X is a K algebra. What is a K algebra? It's an algebra. Well, yeah, you probably know what a K algebra is. So I wouldn't say much, but it's something that K acts on. So like acts on in a yeah, whatever. So yeah, this is the main theorem I want to present today. So theorem, like K be an algebraically closed field, and there is a natural fully faithful functor from varieties over K to schemes over K. So what it's saying, what does fully faithful functor mean? So it means that if I have a map between X, Y, you can find the same map over here as schemes. And there's a one-to-one correspondence between maps from X to Y to maps from T of X to T of Y, where this happens in the world of varieties over K, and this thing happens over the world of schemes over K. And additional statements are for any variety V, its topological space is homeomorphic to the set of close points of the underlying topological space of TV, and its sheaf of regular functions is obtained by restricting the structure sheaf of TV via this homeomorphism. So I want to, before constructing T, I might just use a blank space to give some consequences or reasons why I think this actually gives me a little bit better understanding of what is going on in the world of schemes. So first, sorry, first, you may notice that, okay, in the world of varieties, let me just draw something down. So say this is your say this is your C2, say this is your C, and then like okay, I have a point. So points in C, which remember it's K adjoint X, which sorry, C adjoint X, and this is the coordinate ring for C. So uh, uh, the affine one space is corresponds to this coordinate ring. And maximal ideals, so a point here, let's say, call this A. So points over here actually corresponds to the maximal ideal Z minus A, right? This is a maximal ideal, and all maximal ideals are prime. And in the world of spec, we consider spec of CX. Well, we are a little bit unlucky because in this ring, it's actually a PID, so maximal is equivalent to prime. But what I'm saying is in other spaces, when we consider prime ideals, this actually adds more points other than prime, other than this maximal ideal. So the slogan is schemes contain more points. So like in the world of varieties, any irreducible subset by the following description of my T functor actually gives you a point in the world of schemes. So it actually gives you more points. But interestingly, the topology doesn't change because there's an open there's a correspondence that I'm going to talk about between open subsets of X and open subsets of T of X. So it doesn't change the open sets, but it does add some extra points, so the picture looks a little bit different. Um, and I want to argue that okay, let me see what's going on. Yeah, so why? Okay, so just be careful in the world. I might just explain this a little bit. Um, so in the world of schemes, I have spec of A. Suppose I have a prime ideal inside it. Let's look at this closure. So P closure, the closure of the one element set P is equal to V of P, which I defined to be the set of prime ideals Q prime such that P is included in Q, right? When Q is max, so like what does it tell you? So P's closure is equal to P, or in other words, is a close point if and only if P is maximal, because there's no other non-trivial, not like ideals, which is not the whole ring that contains P. Um, so yeah, so close points correspond to maximal ideals. So this gives a justification of this part, sort of why intuitively this should be true. Um, and so like the following this second part of this statement just makes a little bit more sense after I explain this part. I feel like so let me construct this T right now. And it's a really brief construction. For details, you can consult Harshorn. This is Harshorn proposition 2.2.6, which is in the second chapter of schemes and second section. And then it's the proposition 2.6, if I remember correctly. And so let X be in any topological space. I can define T of X to be the set of non-empty irreducible closed subsets of X. So these observations will convince you that if I can put a topology on T of X by taking as closed sets the subsets of the form T of Y, where Y is a closed subset of X. And this is the interesting part. So as I mentioned before, I told you that the set of open sets, it actually like the topology didn't change, but you okay, Shimo, you claim that you added extra close points. So the space should be larger. Why is the topology still the same? Well, when I talk about topology, I'm talking about the set of open sets. So even though I added a little bit more points, this mapping to T of X by P mapping to the closure of P actually induces the correspondence between X and open set T of X. So by this, I have a natural T structure on X, which is the T of regular function because of X. Now I take it to be a variety. Uh, there's a natural structure sheaf O of T of X on T of X just because of this correspondence. And now the K being an algebraically closed field, alpha variety Z of I as a subset of AN has a corresponding affine scheme taking the spec of the coordinate ring. And I claim this could be T of X. Um, so, okay, so I've claimed also the part that T is fully faithful. So why is that? So for X equals V of I and Y equals V of J, both affine varieties, we have homomorphisms between X and Y as varieties over K is equal to homomorphisms of K algebra of the regular functions, and which is a theorem. And then this actually, I have a duality. I have this correspondence between schemes and commutative rings, which I just defined above by taking the spectrum, but it kind of reverts. It makes the arrow goes the other direction. So this is where this equality comes from. And I think this will be the end of my talk. So I appreciate everyone who would help me. A lot of helpful conversations that I really enjoyed uh, talking to people during and after the presentation. Unfortunately, my the I got a really harsh time limit on my old presentation, which I know it's really administrative, but this is why I decided to record it again after I came back, and I hope this helps. So thank you.